Okay, good morning. I'm Elaine Hubal with the U.S. Environmental Protection Agency with the Office of Research and Development, and I think we were co-sponsors on the report, famous report. But I'm thrilled to take a little time off and catch up on this research area. It's fascinating and incredibly important. So this next session is implications of microbiology, the built environment for health and design. And so I think that was sort of the catalytic point of this entire investment is so now what do we do? And the first speaker is Shelly Miller from University of Colorado, I think. So I can come down. I'd rather.
While we're getting this going, I wanted to just say I'm one of the environmental engineers in the crew, so I'll be speaking engineering language, which I've really enjoyed working with the building scientists, of which I work closely, and also the biology folks to really learn so much about this field. And what I wanted to talk to you about today is the intersection of environmental controls with the microbiology of the built environment. I don't think we're yet at the point of figuring out quite how to make them work together, but I'm going to give us a start on that. All right, great, thank you. So as I said, I'm an urban air pollution engineer. I study air quality, including indoor air, to ensure that the health of the building occupants is not compromised. To begin defining a healthy building, we must understand what indoor exposures may cause adverse health effects. And so far, we are exploring the microbiome from a point of what is it and what does it look like, and we have a little bit of information on adverse health effects, but not much. But we have a lot of information about environmental pollution and the adverse health effects that we can encounter. So I'll be touching on 3 methods that engineers use in buildings to reduce or eliminate indoor harmful exposures. And my remarks are geared generally towards controlling particulates, gaseous and disease-causing organisms in the environment, whether they are on surfaces or in air. And we know, for example, PM 2.5 causes increased mortality and morbidity. Exposure to ozone and nitrogen dioxide also increases cardiac issues and cancer and other endpoints. The microbiome, on the other hand, right now we are focusing from an environmental engineering perspective is how does it cause disease transmission. So starting with ventilation, and I appreciate what Jessica Green gave you a primer on the work that she's been doing with ventilation. I'll speak a little bit about her work. But the most authoritative American work on minimum ventilation estimates for building came from J. Billings in the late 1800s. So we started to argue that we need higher ventilation rates because he was concerned about the spread of disease. That's where this whole ventilation idea started from. Historically, we've been arguing for ventilation, whether it was to solve odor problems or to solve disease transmission problems. And we approach this by increasing the amount of indoor air to a space. We've now reached a point where, I want to make one important point, is that we now have reached a point where we really need to take into energy efficiency ideas. Mechanical ventilation of buildings is very energy intensive. With increasing concerns regarding depletion of fossil fuels, global climate change, and CO2 emissions, it's important to note that 41% of the US energy consumption is attributed to buildings. How do we usually ventilate buildings? Well, we bring in air through natural ventilation. That's typically used in houses. It's a very inefficient way to ventilate a building. We also do it through infiltration. This is also a way to ventilate a US home, and this is also incredibly inefficient. And then for office buildings and other facilities, we'll do mechanical ventilation, which can be very energy intensive. This is a summary again of Jessica Green's study where we looked at the differences in the microbiome between mechanically ventilated buildings in a hospital and windows open and compared to the outdoor environment. And what we see is that the community composition is very different between the window ventilated room and the mechanically ventilated room, and there's some overlap that looks very similar to outdoor environments. So what we want to try to think about is when we're ventilating a building, do we want to bring in clean outside air that has the microbes in it, or do we want to also clean that air through some filtration mechanism, for example? And that's one question that I'm interested in exploring as it relates to the microbiome, because if you filter out PM 2.5, you're also filtering out some airborne microbes as well. I just want to summarize for you the plethora of data on ventilation rates and health. It's very clear from the research that higher ventilation rates are associated with reduced prevalence of sick building symptoms. It's also associated with reduced inflammation, respiratory infection, asthma symptoms, short-term sick leave. All of this is related to ventilation rates. And if we can get the ventilation rates up to 25 liters per second per person, we see these health endpoints improved. We see also that home ventilation rates above a half air changes per hour, which is pretty high for a US home, typical home these days. That's been associated with reduced risk of allergenic manifestations among children. Recent unpublished data from my research group is showing a strong association between better lung function and homes that are more leaky. So we know we need ventilation. Is it the microbiome that's helping to mitigate some of these health effects, or is it the fresh air, or what exactly is it? I wanted to reference the study coming out of Jordan Petchia's lab that showed low fungal diversity in house dust is associated with childhood asthma development. And the top graph shows the differences between, on the right-hand side, we have the controls, which are the children without asthma, and here's the cases with asthma, and we see that the asthma cases have lower fungal diversity. On the other hand, one indication of interesting association is that you have higher fungal diversity with more moisture indicators. This is a very interesting piece that I wanted to point out, because if you want to change the type of fungi where you are exposed to in your home, then you need to actually move, because the fungi you're exposed to in your home comes from where you live and from outdoors. So if we're ventilating our homes and our buildings with diverse fungi-rich air, is that impacting the health of the occupants inside? And I think it's a really interesting question, whereas high diversity of fungi in house dust is important for what we see here with the asthma study. So many questions still related to ventilation and the microbiome of the built environment. How about filtration? It's been used for decades to remove particles and chemical contaminants from air streams. We know that fiber filters, such as HEPA or near HEPA filters, are very effective for reducing home contamination. And we also use it in buildings to clean the air prior to ventilating, although most building filtration systems are pretty coarse and are not designed completely to remove PM 2.5 or airborne microbes. Gaseous filtration, we use things like activated carbon to remove ozone and nitrogen dioxide, and we know that this is important in highly polluted environments, such as the developing world with cities in India or in Shanghai, for example, where we have very high PM 2.5 and we need to clean the air before it comes inside. You know, currently there are no standards for air cleaners, so I get questions all the time about which air cleaner should I buy, and it's actually very confusing to the consumer. There is a voluntary certification program that you can look at to see whether your air cleaner is going to work in your home. This is the Association of Home Appliance Manufacturers certification, and it will give you the clean air delivery rate. And this label up here, for example, shows you that this air cleaner will clean 120 square feet. Well, that's not a lot of space, so if you have a 500 square foot space you're trying to clean, you need to buy 5 of these, for example. Also, I really think it's important to point out that many air cleaner designs do generate ozone, which you don't want in your house. And thankfully, California has stated that all air cleaners sold in California will meet an ozone emission, although it is at 50 ppb, which in my personal environmental engineering opinion is a little bit high. These are some studies we've done out of our lab where we showed that using an air cleaner in your house during a wildfire is much more effective than just sheltering indoors with your windows closed. We found indoor concentrations of PM2.5 to be reduced by over 80% with your air cleaner, whereas when you're just in there closing your windows, it's only about a 30% protection effect. So with wildfires and somebody who has respiratory issues, we definitely recommend air cleaners. This other graph is from one of the very first papers I published in the late 90s, and what I wanted to show here is that if you ventilate a building with 6 air changes per hour, you reduce the concentrations by about 50% of your particulate matter inside. If you use portable air cleaners, which are going to give you 4 air changes per hour filtration plus 2 air changes per hour ventilation, you get about the same effectiveness. Or you can use ceiling-mounted air cleaners that will give you 6 air changes per hour filtration. And again, the efficacy will be about a 50% reduction in your concentrations. And this small graph shows a prediction that if you use a non-HEPA filter as a recirculating air cleaner in your house, it's just as effective as a HEPA-related filter. That's not going to be the case if you use a straight flow-through filter in your HVAC. I wanted to point out this graph because there's always some question as to whether bacterial particles perform the same as chemical particles, and yes, they do. These are all data from different air cleaner measurements showing that whether you use a bacterial aerosol or a chemical aerosol, they're all equally as effective. There's no statistically significant difference. And this is because the major factor affecting particle capture by a filter is its aerodynamic diameter, determined by the particle density, shape, and physical diameter. So that, in fact, when you see an airborne microbe, it's just as if it was a regular particle, and we'll treat it the same way as an environmental engineer. So what I usually recommend for air cleaners is that, yep, they do work. You need to know what you're buying. You need to buy enough to cover the square area that you're treating, and you need to make sure they don't generate ozone, which typically can be done by not buying an ionizing system. The last technology I'd like to hit upon is UV lamps. We've done UV lamp research since, I don't know, for the last 20 years. And we usually use the UV lamps to disinfect upper air or disinfect surfaces or disinfect air in ventilation systems. And you don't see them very commonly used in the US, but they are very effective for certain applications. And what are those applications? This is some photographs of using UV as upper room lamp fixtures where they irradiate just the upper space of a room, and then they do not irradiate the lower space, which is occupied by people. That way you're not exposed to the UV radiation, but yet the air mixing will bring unsuspecting microbes up from the occupied zone into the upper level of the room and then disinfect the air in a recirculating mode. These are very effective lamps when you have high occupancy environments and you have unsuspecting disease transmission possibly happening. These are now UV robots being used in hospitals to disinfect surfaces. One of the issues is that many hospitals don't yet know how to deploy them effectively, and also there is a shadowing effect that we need to account for. We can also use them in HVAC systems to disinfect components like the cooling coil, or we can use them in duct to disinfect air as it flies through the vent. Just some data from our group to show you the kinds of research we've been doing on this, which is that our data is published in a NIOSH design guide for upper air UV, and we do see there's a relative humidity effect. If you have high relative humidity, your efficacy of UV decreases. And similarly, we see that both in inactivation rates and effectiveness. And this is because of the differences in the DNA conformations when you have a high relative humidity environment, we think, compared to a low relative humidity environment. And I am almost done, I'm pretty sure. We're going to reduce concentrations of airborne infectious microorganisms by 50 to 90% with UV. We can interrupt the transmission of tuberculosis. It's very well proven against airborne disease such as TB. We've also seen it to improve worker symptoms in office buildings. We have seen one study on lung function of asthmatics. I'd love to see this repeated because this is quite intriguing. It does alter the spread of measles in schools, and a very nice study on NICU-associated pneumonia showed a significant impact on the baby's health. We also see room surfaces decontaminated with UV. So there's a lot of promise from UV. So I'll just end there because my time is up with this summary slide for you, and thank you for your attention.
Is there one quick question? Yeah, there we go.
Hi, thank you, Shelly. Just a quick question. Is there data on the chemistry effects of having these indoor UV lamps?
There's not a lot of data on the chemistry effects of the UV from the air disinfection wavelength of 254. Most chemistry that we have studied has been at the smaller wavelength of around 180 or so. So I think it's an interesting question. We haven't seen a lot of data on that